Good morning, everyone. So welcome to our lecture class. So Physics for Engineers, Vectors and Kinematics, Part 4, Basic Vector Calculus. Okay. So we're going to apply now your calculus knowledge. Okay. So what you've learned from your calculus class in our problem solving. I think it's not that hard naman because if you understand how kinematic variables are working, for example, position, velocity, acceleration, their relationships, and then we also tackled about the motion graphs, uh, where uh, where I illustrated the connections between these variables. It would be pretty basic to understand, or pretty easy to understand how does your vector calculus works. Okay, so let's dig in. So these are the basics of vector calculus. Okay. So we start with derivative of vector functions. Okay. So let's say we have a three-dimensional case. So it's a general case, a three-dimensional case, whereas your coordinate system is defined by, of course, I, J, and K, as you can remember. Then you were given with three vectors here. So what are these three vectors here? So let's say you have a vector function. When I say a vector function, it is a vector that is dependent on some scalar or some variable u. Okay? So you define this vector a that depends on u. So this yellow vector here. And then let's say you change the value of u, okay, by some value delta u here. Okay. So if you change the value of your u, you add some delta u in it, you expect that since the vector A depends on u, whatever the changes that will happen on u will also happen to your vector A. That's why when you add delta u into the u, okay, it will have an effect to vector A and it will change. So this green vector here would be the result. Okay, so this is your vector A that changes relative to the change in u. And if you try to look for how much does your vector A changes, this this vector here, this delta A vector here, will show you the change in that vector. Okay, so these three vectors tells us how does a certain vector changes. Okay, and uh, uh, how does the variable affects. Okay, so let's say the variable u affects vector A once variable u changes. Okay, and if you look for the form of delta A, okay, if you try to make an expression for delta A in terms of your original vector A and your vector A that have changed because of the addition of delta U, this would be the form. Okay. So the delta A here, or the change in your vector A, is equivalent to the difference. Okay, difference between the final state of your vector, okay, and then the initial state of your vector. So again, this change in vector A is equivalent to the difference between the final state of your vector and your initial state of your vector. So the final state is u plus delta u, okay, and then your initial state is u. So this is your expression. And this expression is really important, okay, because somehow this expression is similar to what you've been using in your calculus. Okay, so if you have a function, let's say f of x, and then you change x by some value delta x, therefore the change in the function would be equivalent to f of x plus delta x minus f of x. And as you can remember in your calculus class, that expression, okay, is vital actually. It's vital for your understanding of derivatives. Okay, so let's go to the next slide. Ayan. So if you ask, what is the derivative of the vector, okay, of your vector A with respect to u? So when you say derivative, you are looking for the change of a certain vector here, okay, the derivative of a vector. How much does your vector A changes with u? If you change u, how much your vector A changes, how much it affects A. So that's what you want to answer, that kind of question when you want to look for the derivative of vector A. So getting the derivative of vector A, so let's say delta A over delta U, okay? So delta A and delta U are like somehow huge numbers. So if you take the limit of your delta U as it approaches to 0, you are now getting the infinitesimal dA over du. So dA over du, as you can remember in your calculus, the definition of your derivative is getting the slope, okay, and so on. Of course, hindi pa tayo nag-graph ulit. Okay, so these are just a physical representation of your vectors. But anyway, so let's continue. So in the form, the derivative of your vector A is equivalent to, with respect to u, is dA over du. Okay. So since delta A is equivalent to AU plus delta U minus AU, okay, over delta U, this would be the expression for your derivative of your vector A in terms of the limits, okay? If you can remember your topic about the limits of the function, so ito yung tsura niya, di ba? So if you have f of x as a function, and then f of x plus delta x minus f of x over delta x, and then you take the limit of that expression, you will get the derivative of your f of x. In terms of your vector functions, parehas lang. Okay. So the derivative of your vector function AU with respect to DU would be expressed using this limit. So just remember this. So next. Okay, so as a review, ito sabi ko kanina, okay, from your scalar functions. Okay, so you have two types of functions. Actually, there are many types of functions, but in this scenario, in our case, we have scalar functions and vector functions. Of course, your scalar functions are your well-known functions. Okay, it's just involve numbers. It maps your x to y or so on. U to x, U to y, U to z, because your u is another dimension. Your u can be time or some other variables, but in this case, if you have this x, y, and z, your x is like a function of u. That's the idea here. So your x is a function of u, y is a function of u, and z is a function of u. Okay. So scalar functions, you don't need, of course, your basic functions will suffice. And the difference between the scalar and vector functions, of course, vector functions needs direction, or you are dealing with vectors in general. Okay, so if you have, as a review, as you can remember, okay, so ito, you have your x, so you have your y, and you have your z. So ang ginawa ko dito, pinattern ko siya sa three coordinate system. So you have the x, you have the y, and you have the z. And as you can remember, okay, doon sa ating motion graphs, kung babalikan natin yung motion graphs natin, so let me get first my tablet. If you can remember our motion graphs, oops. Okay. So sa motion graphs natin, you have two axes, okay? For a one-dimensional motion case, you have two axes to describe the motion of the body. The first one is the time axis, and the second one is your let's say this would be the x-axis. If we replace this x by y and by z, it's just the same. Okay? So technically, okay lang na palitan mo si x ng y and z. It means that your object is moving along the y-axis or the object is moving along the x-axis, and still it would have the same principle, okay, or the same basic process of how you understand the motion of the body, and this would be the time axis. Okay. Or let's say not the time, but some arbitrary valued number u or variable u. So x is dependent on u, y is dependent on u, and z is dependent on u. Okay. Of course, your u is just a placeholder. It can be time or whatever variable you want to. Okay. So let's go to this one. So a review of your derivatives. Okay. So let's say you have this curved line here, this blue, faded blue, okay, line here. So this faded blue line here is your function, okay, x of u. So your x of u, and then this is your axis u. And as you can see, this faded blue line here tells you some function x of u that we didn't define, or we don't define here. We just graph it and so on. Okay, so the question is, what would be dx over du? Or what would be the derivative of your x of u with respect to u? So when we talk about derivatives, we are getting the slope of the line. Remember, the slope of the line. So let's say you define 2 points, u1 and u2. So u1 is the first point, the second point would be u2. And of course, you tried to look for the change in your value of xu by u1 and u2. So at x equals u1, this is the point, and at x equals u at u equals u2, this will be the point in the function. Okay. So if you try to plot a line, a straight line that passes these 2 points, you will get this green line. And if you ask what would be the slope of this green line, okay, you need to solve for the equation of the line. So what's the equation of the line? This one. Okay. If you look for the slope, you derive the slope, you have this expression. xu2 minus xu1 over u2 minus u1. Okay, so I think it's pretty clear. It's a basic knowledge for those who are studying calculus. Then what we're going to do is to reduce the size or the distance between u1 and u2. So what we're going to do is to put u2 further towards u1, so that the difference between u2 and u1 will be close to 0. So if we do that, okay, so again, the distance between u1 and u2 is delta u. Okay, so the u2 minus u1, again nyo sa kabila yung u1, so you can see that u2 is equal to u1 plus delta u. Yeah. Okay, so for clarity, you can also change that dun sa x. Tada! So xu2 is equal to xu1 plus delta u, u1 plus delta u. So dito nang galing yung inyong definition na nito, dito sa taas. Okay. So x is dependent on u, so whatever changes on u will have an effect on x. Okay, so what will happen if this delta u approaches 0? So you should watch the green line. Okay, how does the green line changes over the change in u? Okay, so let's look at it. Okay, so binaba nyo. So mas maliit na yung delta u nyo ngayon. Lumiit pa lalo. And then lumiit pa lalo. Okay, and lumiit pa lalo. Okay, so nung lumiit siya na lumiit, ano nangyari? Okay, balik natin ulit. Also look for the slope of the green line, ha. So ito yung slope ng green line nyo. Then nung lumapit, medyo tumaas, medyo naging steep, and then pa-steep siya ng pa-steep. Okay? Until at the end, Okay, maliit na yung delta U nyo. So, you change your delta U now into du. Okay, du is the infinitesimal change in U, a very small change or a small amount of change in U. So, we can just replace delta U with du. Okay, when delta U approaches to 0, U1 and U1 plus delta U will be almost the same. Okay, remember that. Kapag masyado na siya malapit, of course, they are not equal, they are not the same, but almost the same. Okay, and that effect will also happen for your x, okay, for your function xu. Okay, but take note that we are more interested with this green line. We are not that interested with the small change in u or small change in x alone. We are interested with both of them, okay, and the ratio of them, the slope. Okay, the slope of this green line will be the ratio of the small change in the function of u, which is dx, and your du. So, so this one. Therefore, as the value of delta u approaches 0, you are taking the limit of the function of the green line. Okay, the slope, the slope of the green line. And the slope tells you about the derivative. Okay, so substituting the expression for the slope of the green line. Okay, so this one is your derivative of your x. Okay, so again, so ito, pinaliit ko na siya. Yan. So this green line is now tangent to the blue curve. So this faded blue curve and this green line, okay, if you take the derivative, this point is the point of tangency. Okay, so this line is now tangent to the curve. Okay, and if you get the slope of this tangent line here, you are technically getting the derivative of this function. Okay. The slope of the tangent line is your derivative. So again, this is just a review of your calculus, and this knowledge is really important for us to apply it in our kinematics problem. Okay, next. So we generalize. Okay, so let's say you have this curve. Okay, so all of these green lines are all tangent lines, as you can see. Okay, and you can take the derivative, okay, of the derivative of this curve at different points. Okay, take note that derivatives or differentiation is what they call a local operator. Okay, when you say local operator, you need to take into consideration at what point you're going to take the derivative, at what point you're going to take the slope of the tangent line. Okay, in opposite to integration, which is a global variable, because you are taking the area or the volume of entire which take up space. So ito, you need to define a point, okay, where you look at the slope. When you take integration, you are talking about certain area, okay, certain bounded area where you're going to get the area, where you're going to apply the operation, which is integration. Okay, so for derivatives, okay, all of these green lines are, yes, tangent to the curve. Okay, so let's say find the derivative at this point. Let's say u1, and u2, u3, and so on. Okay, so now we've reviewed that. We're going to apply that in our vector functions. Similar lang naman. So from scalar, you just go to the vector functions. These creatures here, x, y, and z, will become vector value. Okay, so as you can remember, in your calculus class, you have different useful identities for vector functions. So you have this one. So if your m, okay, if your m is also a function of u, if this is okay, if this m is a function of u also, okay, it means that your scalar variable m is a function of u, then this one would have a value, okay. But if not, okay, if m is just a constant, then you try to derive it with some variable u, this one would be equal to 0. But in general form, the general form would be this. Okay? So product rule. And then if you add two vectors, then you take the derivative of the sum of these two vectors. It's the same as applying the derivative individually to both A and B. Then you have a dot product. Okay? So the derivative of your dot product between A and B would be equivalent to this one. So product rule. Okay? So so A dot the derivative of your vector B with respect to U plus the derivative of your A with respect to U dot B. Okay? Take note that A dot B is commutative. So pag nagbaliktad sila, parehas lang. Okay? You reverse the order, they are the same. So whether it's dB over du dot A or B dot dA over du, walang problema. Okay. Pagdating mo naman sa cross product, yun ang problema. Okay? So using using cross product or getting the derivative of cross product between vector A and vector B, okay, you must ensure of their order because remember A cross B is not the same as B cross A because there's a negative sign here. Okay? So the anti-commutativity law or property. So again, applying your product rule in this case. So vector A cross dB over du plus dA over du cross B. So these are useful vector derivative identities that you need to remember. And of course, okay, itong nasa una, medyo useful to, okay, because MA, scalar value, okay, and your vector function, you multiply your scalar to vector, it's like it's your scalar multiplication, remember? So let's say B is equal to M. Oops. Nangyari. Wait lang. So it's like you have vector B, you scale some vector A by a certain amount C. Okay. So remember scalar multiplication. Okay. And remember that in your high school physics, you have your Newton's laws, right? So remember that your F is equal to MA. F is a vector. NA is a vector also. Your acceleration is a vector. And then your mass is a scalar value. Okay. Scalar. So let's say there would be some value U, let's say dF. Let's say we derive dF and we try to take the derivative of F with respect to T. Okay. You don't need to be bothered with that. Paano yun sir? Pwede ba yun? Okay. You just don't need to be bothered with that. Okay, just follow me. Okay, let's say you take the derivative of F with respect to T, then it will also apply to your MA. So d dt of M. Okay. So, and then you can apply this rule so that you will have this one. So M dA over dt plus dm dt A. Let's say your M, okay, let's say your M is a function of time. It means that the mass of whatever object it is changing through time. Then this term should be in bold. Pero kung inyong mass is constant, you just cancel it. Okay. So yeah. So ano lang yan example lang yan. It's not really a well-defined variable df over dt. But there is one, okay, that has the same form. Okay. In our intro to physics, as you can remember, we tackled about momentum. Okay, momentum is equal to mv. Okay, so take note again. This is a vector, and this is a scalar. If you try to get dp over dt, so this is a valid expression. Okay, the change in momentum over time, it will form d dt of mv. Okay, and d dt of mv would give you, well, force. Paano naging force? Okay, as you can remember, dun sa ating intro to physics class, so d dt times mv, let's apply this product rule here, it will become m dv dt plus dm dt v. What is dv over dt? Your dv over dt is equivalent to acceleration. So this first term is your force term. So m times a. And the second term is also your force term. Okay? The second one is also your force term. Okay? Whether the mass is the one that is changing right now. Okay? So yeah, so that's the general expression for your force. We're going to tackle this one pagdating natin sa dynamics part. But pinakita ko lang sa inyo yung application nito. Because this one has a lot of applications rather than these two or these three expressions. But you must remember all of this. And it's really useful. Okay. Let's go to the next one. Vectors in kinematics. Okay. So, dun sa ating motion graph, as you can remember, sa motion graph natin, we deal with one dimension only. Okay. So one-dimensional motion, a motion along the x-axis or along the y-axis or along the z-axis. Now we try to generalize it, okay, with a two-dimension or a three-dimensional motion. So we're going to do that. So first, okay, position vector and displacement vector. So let's say this blue curve here, okay, is the path or the trajectory of this black dot. So your black dot is moving along this path, this trajectory. So of course, this trajectory is some function of time. Okay? So nagbabago yung iyong position over time. Therefore, your position is a function of time. And you call that function as RT. Okay? So RT is your position vector, okay? Position vector of the particle at time t. And take note that this position vector was defined using some frame of reference. So let's say that this reference frame here, this is the origin of your reference frame, defined by x hat and y hat, is used, okay, to define the position vector. So the position vector would start from the origin, then towards to the position of the body, of the block dot here, okay, which is at point A. So next, after some time, okay, you change the value of your t, so your point A move at some point B. Okay, so that's the idea. So at the change in time delta t, your object moved from A to B. So the position vector r of t plus delta t would look like this. Next, so the change in position delta r would look like this. So the change in position between A and B would be delta r. And then this delta r is equivalent to the difference between the two position vectors that we defined earlier. So RT plus delta t minus RT. Ayan. Okay. Let's say we try to define some fixed point E. Okay, this fixed point E here. So you have your position vector, your RT, and then your RT plus delta t. and you will have a displacement vector. Okay, what is the displacement vector? Remember our definition of displacement? It is the difference between the final position and the initial position. So the displacement vector must define that straight line distance between 2 points. Okay, so delta r can be considered as your displacement vector, or delta r is what you call the displacement vector, which has the same expression as this one. Now, we try to define some point, fixed point E. Para saan? Let's look. So, let's say this fixed point E, okay, that we define will be some kind of basis. So, from this fixed point, okay, you move from this fixed point towards this point, point A. And then you take some distance, the distance that is represented by this red line, and you call it as ST. This ST is what you call the path coordinate. Okay, this path coordinate is also a function of time. Take note, we are taking the distance, so we are taking S. Okay, we are not taking the displacement in this case. We are taking the distance traveled from fixed point E towards E. Then, what would be the path coordinate at some time t plus delta t? That would be S of t plus delta t. This violet line. So you draw a violet line from the fixed line towards B. And then the change in the path coordinate would be delta S. So you have a displacement vector, delta R, and you have delta S, which is the change in path coordinate. Take note that in terms of the magnitude, your delta S in this case is much longer, or it's longer compared to your magnitude of delta R. Because in this case, we are taking into consideration the entire path taken of the body. Okay. So take note again, ulitin ko, in this case, your delta S, okay, is greater than the magnitude of your delta R. Okay. So you have these two expressions. Okay. For the displacement vector, that would be delta R, and for your path coordinate, that would be delta S. Okay. Next. So since na-define na natin yung ating displacement vector and your path coordinate in 2 dimensions, let's go to your speed and velocity. Okay. Again, velocity is the rate of change in the displacement. Okay. So you have your displacement delta R. Okay. And then how much does it change over time? That would be your velocity. And in symbol, this would be the limit of the function delta R over delta T as delta T approaches 0. Or you can also write it as R T dot. Okay. Remember, sinabi ko sa inyo na yung kapag kumuha ka ng derivative, okay, if you take the derivative of a certain vector, okay, dito na pala, nasulat ka na pala, patawid pala. Okay, so R dot, okay, or R of T dot is equivalent to dr over dt. When you take the dot, it means that you are taking the derivative of that certain function with respect to time. Remember, in your calculus, you have your, let's say, f of x dx is equal to f prime of x. Get the second derivative, okay, of your f of x will give you f double prime of x, and so on, f triple prime, and so on. For anything that is derivable with time, differentiated with time, I mean. So dr over dt, or second derivative of r with respect to dt. Okay. So lahat yun is represented by for dot and double dot. Double dot would be the second derivative. Triple dot would be the third derivative, and so on. Okay, so as of now, I need to establish the concept of your velocity as a derivative, okay, of your displacement. So take note that v, velocity, is the derivative of your vector function r, okay, over dt. You can write it as this and as this. Okay. So take note that as delta t approaches 0, the displacement vector becomes tangent to the path. Okay. Next step. Next step. Next step. Ayan. So almost. Okay. So delta r, again dr, and then delta t becomes dt, infinitesimal change. Okay. So take note, this makes velocity also tangent to the path. This is a very important concept. Okay. So this vector, this velocity vector at this point, okay, is now tangent to the path. In this case, we are now taking the instantaneous velocity. So instantaneous velocity. So we're now taking the velocity of the black dot at an instant. Okay, at this small change, very, very small change in time. So it's almost at this moment. Okay. Okay. Also, meron ding ano dito, note. So take note. Kanina, excuse me, this is the vector expression. Ito naman, if you take the magnitude of your velocity, excuse me, if you take the magnitude of your velocity and you take again the magnitude of your displacement vector, which is the absolute value of delta r, and you take the limit of delta t approaches 0, napansin nyo, you are getting now the path coordinate. Okay, so you are now solving for the path coordinate and its derivative over time. Okay, so the magnitude of your displacement vector becomes your delta s. Okay, the magnitude of the velocity is speed. Okay, at least the instantaneous velocity. The magnitude of your instantaneous velocity is the instantaneous speed. Okay. So again, speed is a scalar quantity, velocity is a vector quantity. Oops. Yeah. Okay. The next, we have acceleration also. So let's look at these two velocity vectors. So vt and vt plus delta t. So let's say your velocity changes. Remember, ilang beses ko sinasabi that when you have an acceleration, there's always a change in velocity. If there is an acceleration, there's a change in velocity. Okay. So if you want to get the change, okay, so you take your vt and your vt plus delta t, and then you technically subtract them. Vector subtraction. So ang ginawa ko, kinuha ko yung dalawa, subtract ko yung dalawa, and then you will get this expression, vt plus delta t minus vt. Oops, sorry. Okay, again. Nulit-ulit ko lang para makita nyo. The next, okay, the rate of change in velocity is the acceleration, and you have these forms. So all of these forms are valid. So your at is equal to the limit of your delta v over delta t as delta t approaches 0, which is also the same as the dot. Okay, vt dot, which is equivalent to dv over dt, and it is also equal to the to rt double dot, okay, which is the second derivative of your displacement vector or position vector function with respect to time. Oh, this is wrong. Should be here. It's not here. Sorry, mali yan. Should be, ngayon ko na napansin. So, dr. Okay, so the second derivative of your position vector with respect to time. Note, unlike displacement and velocity, acceleration is generally not tangent to the path of the particle. So, ano ibig sabihin ito? It can be tangent in some cases, it cannot. In some cases, it's not. So not all the time is that your acceleration is tangent to the path of your particle. Take note that in this case, okay, at some time t, okay, your velocity vector is tangent. It's always tangent to the path. Of course, for vector b, it's the same. Your velocity vector is tangent to the path. Okay. But for acceleration, it's not always. As you can see, oops, sorry. As you can see here, sorry. Okay, as you can see here, this green vector here is neither tangent to the green line, neither parallel to the velocity vectors at any time at all. So in this case, your delta v here, which is change in velocity, divided with the change in time, you will get the acceleration. This vector here is not tangent to both A and B, not tangent to the entire path. Okay. So it's not necessarily mean that your acceleration is always tangent. It can change its direction anytime, depending on the velocity and position of the particle. Okay. Next, kinematics in 3D. Okay. So in 3D, you have this one. So you define x, y, and z. Okay. I, j, and k. And then this side would be x. This side would be y. And this height, the height would be z. So if we try to define a position vector in 3D space, okay, take note 3D space. So kanina nasa 2D lang tayo, ngayon nasa 3D na tayo. So if you try to define the position vector of this red dot at point A, you need this expression, xi hat plus yj hat plus zk hat. Take note, okay? Take note that the origin is 0, 0, 0. It means that your x naught would be equal to 0, y naught is equal to 0, and z naught equal to 0. All of those are your initial position. And then this point A would be like your final position here, described by xi hat plus yj hat plus zk hat. Okay. In general form, the general form for this one, let's say your vector is not on the origin. Your initial position is here. The initial position. And your final position would be this point A. Let's say this point A lang. So this vector would be your position vector. Okay. So the reference would be this some initial point, which we don't know. Therefore, let's say this is x naught, y naught, and z naught. Okay. Hindi pala, mamaya pala to. Nagkamali ako, sorry. We should not define it like this. Mamaya pala to, the displacement. Okay, tama, pwede. Nabura ko patuloy. Okay, let's define again x, y naught, x naught, y naught, and z naught. Okay, then the sum vector. So the general form would be like this: x minus x naught I hat plus y minus y naught j hat plus z minus z naught k hat. Take note that your object, let's say you define an initial position x naught, y naught, and z naught, and then after it moved, then nandito na siya sa A with the same coordinates x, y, and z. So in the general form, this is actually what they call the displacement. Okay. I think babalik tayo dito mamaya. I'm not sure. But at least I try to define your displacement vector. Okay. So displacement vector is x minus x naught I hat plus y minus y naught j hat plus z minus z naught k hat. Take note that if your x naught, y naught, and z naught are all in the origin, okay, with the coordinate 0, 0, 0, you will have this one. Okay. So it will have your, this would be just your position vector. Okay. So next, then let's try to define your velocity in a three-dimensional case. So let's say we stick with the position vector, the origin, your vector was referenced from the origin, and then your object is at point A, okay, this red dot, and then this red dot is moving along this path. So the question is, what will be the velocity of that red dot? What will be the expression of that what is the expression of the velocity of this red dot? So from our expression, dr over dt, and your position vector r is equivalent to xi hat plus yj hat plus zk hat. Okay, we operate this time derivative here. Okay. Remember our properties, our identities, okay, our vector function properties. So since you have this expression here, you try to distribute your derivatives for each term, like this one. Okay. So v is equal to dt xi hat excuse me, plus dt ddt yj hat plus ddt zk hat. Okay. And what will happen is this product rule. Okay. Excuse me. So product rule for this term, product rule for this term, and product rule for this term. Okay. And then next, take note that the derivative of your I hat with respect to time, derivative of j hat with respect to time, and the derivative of your k hat with respect to time are all zero. Bakit? Because your I, j, k are fixed coordinates. It means that it doesn't change over time. So it's a constant. Therefore, derivative of a constant is 0. Okay. So all of these terms here now will become 0. And it will give you this one. Okay. This is the expression for your velocity vector. Take note that your Vx is x dot, your Vy is y dot, and your Vz is z dot. So if you go back earlier, ano lang natira? Ito, at ito. Okay, so x dot I hat, y dot j hat, z dot k hat, and that is your velocity vector. Same case as v is equal to x dot I hat, y dot j hat, z dot k hat. Okay, so that is your velocity vector in 3 dimensions. Represented using your I hat, j hat, and k hat. How about acceleration? Ayan, mas komplikado na yung itsura ng diagram. Okay. Kung hindi siya nag-make sense sa inyo, try to review this slide. Okay. Try to review this resource and make familiar. Okay. Be familiar with this illustration. Okay. So remember our definition for V is the definition for your acceleration is the change in velocity over time. So dv over dt. And since you have your v which is equal to vxi hat plus vyj hat plus vzk hat, you take the derivative of each term with respect to time. Okay. Then you will get this one. So parehas lang. So since pag in-apply mo to, magkakaroon ka uli ng gagamit ko uli ng product rule. Okay, magkakaroon kayo ng di over dt, dj over dt, and dk over dt. Since these are fixed coordinates, they will be just set into 0. May iwan lang is this. ddt of vx, ddt ng vy, and dvz ng dt. And these are all vx dot, vy dot, and vz dot. And this is the form of your acceleration vector. Okay, v sub x dot I hat plus v sub y dot j hat plus v sub z dot k hat. Hirap basahin, no? Okay, so this is your acceleration vector. And take note, okay, of this one. Your magnitude, okay, of your acceleration vector or the component of your acceleration along the x, take the magnitude of that, okay, it will be the same as v sub x dot and x double dot, okay, the second derivative of your position. Take note that this one is your a sub x, this one is your a sub y, and this one is your a sub z. It means that a sub x arrow bar would be your x component for the acceleration vector, ay would be the y component of the acceleration vector, and az is the z component of your acceleration vector. Getting their magnitudes, that would be ax, which is equivalent to v sub x dot, and double dot ng x, okay, x double dot. It means second derivative of the x component of the position vector. Whew, daming terms. The same case for ay and for az. Okay? So if it doesn't make sense to you, try to review our previous lectures on vectors. Okay? Also, the motion graphs and the previous slides of this presentation. Okay? So this is your acceleration vector. Okay. As a review again, saan tayo nagsimula? We started here sa position vector. Position vector. Then we take the derivative of that position vector. Then we now have your velocity vector, this one. And then we take the derivative of this velocity vector to get the acceleration vector. So that's the progression of the steps. Position vector or displacement vector in general. Remember this one. Okay. This one. This is the general form, the displacement vector. So from displacement vector, you take the derivative of the displacement vector, take the velocity vector, and get the derivative of the velocity vector, then you will have the acceleration vector. So that's the progression of the step. Okay. Next, planar motion or plane motion. So let's say this is your position vector or displacement vector. The reference from the origin. So x I hat plus y j hat. Okay. So the motion of the object is restricted to two dimensions only, the x, y plane. Okay. And then we define the velocity to be vx I hat plus vy j hat. If we plot it in two dimensions, ito itsura niya. So this is your vx I hat, the x component of your velocity, and vy j hat is the y component of your velocity. Okay. Okay. And then next is that we define the acceleration. Let's say the object is accelerating. So in two dimensions, you have only two components, ax I hat plus ay j hat. Okay. So ax I hat, ay j hat. And this would be your representation graphically. Okay. Next. So Vx is equal to x dot, Vy is equal to y dot, and your Ax and Ay would be x dot, x double dot, y double dot, or Vx dot, Vy dot. So just a legend. Okay. Next, if you try to solve for the theta, okay, first is the theta for the velocity, and your beta would be the angle for your acceleration. You have this expression here. For the tangent theta, that will be equal to Vy over Vx. Vy is your y component, Vx your x component. So this theta would be equal to Vy over Vx, which is equivalent also to this one, dy over dx times dx dt, which in turn the same as dy over dx. Okay. Okay, and then for the tan beta, okay, you got to get the beta, that would be your ay over ax. Okay, that would be equivalent to the second derivative of y here with respect to t over the second derivative of your x with respect to t. So, yeah. So, ganyan yung po kukunin yung beta. Okay? So, actually, we are not going to solve any problems like this one, but at least you have an idea on what it looks like. Okay? If you solve for theta and beta. Okay? And then, from 3D, we go from 3D, and then we go back to 2D, and now we're going back to 1D. So, this one, napakita ko na to sa inyo last time, dun sa ating motion graph, nang ginamit natin itong mismong one-dimensional diagram na to para sa ating analysis of motion by graphs. But as a review, in a one-dimensional case, you call it as rectilinear motion. When you say rectilinear motion, one-dimensional case along a certain line, okay, one line only, I mean a straight line only, rectilinear motion. So this is the origin. You have this point A, and then the position vector would be r is equal to x I hat, and this red dot is following a certain path, this violet path. And the magnitude of that position vector would be your x. How far does your red dot is from the origin? Okay. And if the object is moving towards the positive x-axis, then that would be vi lang. Isa lang yung component niya kasi isa lang siya. Nasa isang dimension lang tayo, one-dimensional motion. Which is also the same as x dot, the derivative of your position with respect to time. Position vector, I mean. And then if your object is also accelerating, then your acceleration is equivalent to a times I hat. And again, this is the form of your A. Hindi na kailangan lagyan ng X or sub X kung na-define nyo naman siya na itong coordinate na to is along the x-axis. Kung along the y-axis to, then this is y double dot. If along the z, this would be z double dot. So technically, this is the easiest. Okay, we all started from here, then we expand to 3D, and then from 3D go back to 2D, and then go back to 1D. Okay, so there's a trick here. So look at this one. So remember that okay. Ano yung sabihin nitong slide ito? Okay, this is an important part of your rectilinear or in kinematics. Remember that most of the time we define our displacement vector or position functions as xt, or let's say the velocity function as vt and your acceleration as at. It means that your position is a function of time. Here, the velocity is a function of time, and your acceleration is a function of time. But is it possible for us to have ax and bx, where your acceleration is a function of position and your velocity is a function of position? Is it possible? Okay. This one will tell us that it is possible that your a is a function, your acceleration is a function of velocity, and your v is a function of position. And if your a is a function of velocity, it can be also possible that your a is a function of position. So how? Remember that our v is defined, your velocity was defined as dx over dt. Okay? So dx, dr siya dapat, diba? So r, dr dt. But since in this case your r is just along the along the x-axis, so you can replace your dr as x. So v, your velocity vector, is equal to dx velocity x position vector and dt. And if you try to redefine, you take the expression for dt, you will have this one. Okay, so dt is equal to dx over v. Okay, ginawa natin fraction yung derivative. Of course, math people would be angry if you do this, but since we are in physics, we can do whatever we want. So we take the expression for dt, which is dx over v. Okay, and somehow remember that your a is also equal to dv over dt. And we take the expression dt from this expression to be dv over a. And since this dt would be the same as this t nangyaring dito, so we equate both of them. We equate these two, and we form this valuable expression. And then what is this? A is equal to the product of b dv over dx. Okay? And this one shows you this expression. A dx is equal to b dv. So, anong importance ito? You are writing the acceleration in terms of velocity and position. So, this expression doesn't involve any variable time, okay? Any time variable. You just have your position. You have just your change in position. Your change in position, your velocity, and that's it. You will get the acceleration. Of course, this is one way to visualize this. Okay, itong dt na to. Pero meron tong formal definition in mathematics. It's more on what they call the chain rule. Okay. So what is chain rule? In your calculus, your chain rule tells you about this. If A is dependent on B and T, remember that your acceleration is a function of time, and also you are getting the derivative of your velocity. Therefore, A is dependent on the velocity and the time. Okay. So if A is dependent on the velocity and time, and your velocity is also dependent on some variable x and also dependent on time, then your acceleration can be also expressed as the one above here, this one. So remember A is equal to dv dt, okay? And of course, your v is also equal to dx dt, okay? By chain rule, you can use this one. It means that your A will be also dependent on X, and your X is also dependent on T, and forming this one. Okay. So that is your chain rule. Okay. So by chain rule, makukuha natin to, this one. So take note that dv dx, dx dt, what is dx dt? Dx dt is your v. Okay? So may iwanan ka lang ng ito. So this one will be equal to v, and then you will have this dv over dx. And then you will have this expression. A dx is equal to b dt. So itong expression na to ay nanggaling sa chain rule. Okay, so remember that. So again, definition of chain rule: if A is dependent on B and T, and B is also dependent on X and T, then A can be also dependent on X and T, forming this expression. dv over dt, dv over dx, dx over dt, forming this. dx dt is equal to v, then A is equal to b dv over dx. Okay, lapit na tayo. 4 minutes na lang. Okay. So integration for vector functions. Okay, let's say you have an acceleration, and that acceleration is a function of your velocity, position, and time. Okay. So your acceleration is a function of velocity, position, and time. And in terms of x, in x terms, in position terms, your acceleration is the second derivative of your position vector function. So this position vector function is a function of your x dot, x, and t. Okay. So let's say your acceleration is a function of time. Okay. From this one, acceleration is dv over dt. We can rearrange the terms and we can take the integration of your dv. Okay. So integration of your dv, you will get v, okay, which is a function of time. And integrating both, integrating both sides, we also prompt you to get the integration of this at dt with a certain, of course, limit from our boundaries from t naught to t. So take note that ito na siya. Ito na yung ating integration form. So if you were given with an acceleration function and you want to get the velocity at a certain point in time, okay, or the velocity function with respect to time, you're going to integrate this expression at dt. Saan ito nanggaling? Dito po sa ating expression a is equal to dv over dt. Okay. So from derivatives or differentiation to anti-differentiation, which is integration. Of course, we can since this is your vt, okay, this is your expression for vt, we can take one step further, integrate vt with respect to integrate vt dt. Okay, so if we integrate vt dt from t naught to t, you will now get your position. Okay, so that's the progression. So from acceleration towards the position of your object over time, you need to integrate. Kapag naman given ka man ng position function and you want to get the acceleration, you need to differentiate. And this one, integrate. Again, integration is a global variable. Okay, that's why you are getting some bounds from t naught to t. Okay. You're technically getting the area. For differentiation, it's a local operation. It means that you only get it at a certain point. Okay, I think we will just stop in case 1. Okay, I will just continue this discussion next time for further cases. Kasi wala na tayong oras. It's already 10:20. Okay? So I will stop the lecture here.